Last week, we started the discussion of using instrumental variables to estimate causal effects consistently. We started with this simple causal model where there is one causal variable of interest and one dependent variable. In the case that X is not randomly assigned, and thus the correlation between X and U is not zero, we know that OLS regression of Y on X will not give us a consistent estimator for beta 1. However, we introduced a variable V that is required to satisfy two conditions. The two conditions are the exogeneity condition, which requires V to be orthogonal to the structural error term U, and the relevance condition, which requires that V and the causal variable X are correlated. When a variable V satisfies these two conditions, it can serve as a valid instrumental variable for this causal model. With such an instrumental variable, we can use the two-stage least square estimator to consistently estimate beta 1. So the two-stage least square estimator is conceptually, it involves two OLS regressions. In the first stage, you regress X on V, and then you get the regression residual from this first stage OLS regression. That regression residual will be an estimate of the exogenous part of X. And then in the second stage, you run an OLS regression of Y on this first stage residual. That way, you will get the two-stage least square estimator, and we can prove that it is consistent. The two-stage so works conceptually. It's useful for us to understand the two-stage least square estimator. However, in practice, you shouldn't do these two stages manually. Instead, you should use the IV regress command in Stata to estimate the beta 1, to obtain the two-stage least square estimator. The reason that you should do this is this command will give you the correct standard error, while manually running the two stages will not give you the correct standard error for the estimator, even though it does give you the correct estimator. All right, so that's the simplest case. Sometimes a random variable may not be a valid IV because it's not exogenous, but it's possible that it becomes exogenous once we condition on a control variable W or a control variable vector W. So that is the conditional exogeneity condition. If a variable V is conditionally exogenous, that is EU given V and W does not depend on V. That is given W, the mean of U no longer is related to V. If conditional exogeneity is satisfied, and if EU given W is linear in W, and also if the projection of X on V and W is a non-trivial function of V, that's the projection coefficient for V is non-zero. If these three conditions hold, we can again use two-stage least square to consistently estimate beta 1. All you need to do differently is to add W as the control variable to both stages. So in Stata, what you do is IV regress Y on X using V as excluded instrumental variable and W as the control variable. So this is what we discussed last week. And today we'll do two things. We'll give basically two examples where we use two-stage least square estimators. The first example is fuzzy regression discontinuity design. So regression discontinuity design is something that we have talked about before, but we focused on the sharp regression discontinuity design, which allows a control variable, a regression, to give us a consistent estimator for the causal effect. Well, with fuzzy regression discontinuity design, that approach no longer works. Instead, we will use the two-state least square. So fuzzy basically means hairy, not this fuzzy, not like crying baby fuzzy. All right, so fuzzy regression discontinuity design, what is it? Still, let's introduce the basic setting of RDD, regression discontinuity design, where there is a simple causal model where the causal variable D is a binary variable, so it's a dummy variable. And there is a continuous random variable W, we call the running variable, and a known threshold, W0, which is a value that W could take. The fact that W crosses the threshold is important for the value of D. So W crossing W0 makes D equals 1 more likely. So that is the basic setting of regression discontinuity. Some of you asked me whether this threshold has to be known. For simplicity, we only talk about the setting where this is known. In practice, if you know there is a threshold, but you don't know what the threshold value is, this threshold can be estimated. And the estimation of the threshold oftentimes is of very good quality, good enough that it can be treated as a known threshold. But for this course, we'll just treat the threshold as known. So in the fuzzy regression discontinuity case, W crossing the threshold does not completely determine the value of D. So D is not equal to the indicator for W crossing the threshold, one way or the other. So D is not completely perfectly determined by W crossing the threshold. However, D is more likely to be 1 for those individuals with W barely over than those with W barely under. So that means W crossing the threshold will increase the probability that D equals 1. So probability that D equals 1 has a jump at W0. Okay. So that's what fuzzy discontinuity design requires. And in this model, in this causal model, the reason that we want to use the regression discontinuity design is basically D is endogenous. D is not only influenced by W, but also influenced by other factors in U. So overall, less regression of Y on D will not give us a consistent estimator for beta 1. And we want to use this special structure provided by the fuzzy RDD to obtain a consistent estimator for beta 1. Now, because it's a fuzzy RDD, so D is not completely determined by W crossing the threshold. So D is not a deterministic function of W. Therefore, this conditional exogeneity condition for D given W is not satisfied. So this is not satisfied for the fuzzy RDD case. It was satisfied in the sharp RDD case. So what this means is that you cannot obtain a consistent estimator for beta 1 by regressing Y on D and W. So regress Y on D and W will not give us consistent estimator for the causal effect. Fuzzy regression discontinuity design is a lot more common in practice than sharp RDD. For example, if a large public university has a known threshold for high school GPA, above this threshold, students are eligible for admission, and below this threshold, they are not eligible. And suppose students in this state may attend other university if they are below the threshold. So below the threshold doesn't mean that the student cannot attend university. And also being above the threshold does not mean that the student attends the university. So because those who are above may choose not to attend the university for other reasons. However, the high school GPA crossing the threshold does make it a lot easier for the student to attend a university. So if we are studying the causal effect of attending university on future income, then the probability of attending university is affected by whether W crosses the threshold or not. However, is not perfectly determined by that event. In order to use a fuzzy regression discontinuity design, let's define a variable V that equals the indicator that W crosses the threshold. Then V is completely determined by W. Therefore, V satisfies the conditional exogeneity condition. So which says conditional mean of U given V and W equals conditional mean of U given only W. So this is satisfied because V is completely determined, is a non-random function of W. So conditional exogeneity holds. In the fuzzy RDD, it typically also satisfies the relevance condition, which says the projection of D on V and W is a non-trivial function of V. So the projection coefficient for V here is non-zero. This is the conditional relevance condition. And it typically satisfies this condition in the fuzzy RDD because expectation of D given W has a discontinuity at W0. Therefore, typically projection of D on V and W also depends on non-trivially on V. Okay, so ED given W is discontinuous at W means that ED given W depends non-trivially on V, right? So that typically implies this relevance condition as well. Although not all the time. There you can find examples where ED given W is discontinuous at this point, but the projection of D on V and W, in fact, is only a linear function of W with no V in there. That is possible, but that only happens in pathological cases. So typically, this is also satisfied in fuzzy RDD. Now, because it satisfies the conditional exogeneity assumption, satisfies conditional relevance. Now, if we also assume that EU given W is linear in W, then from what we learned from in last lecture, we know we can consistently estimate the causal effect beta 1 of D using V as instrument and W as control. So what you do in Stata is to do an IV regress, Y on D using V as instrument, controlling W. So this gives us a consistent estimator for the causal effect if we assume global linearity, but global linearity of this function typically is not satisfied. So the solution, the usual solution is to do a local linear two-stage least square. The local linear two-stage least square only assume EU given W to be a smooth, which means here continuously differentiable function of W around a neighborhood of the threshold value. So if that is the case, if that function of little w is continuously differentiable, then in a small interval around the W0, this function is approximately linear. So that suggests we can restrict the data set, restrict our sample to individuals with W in a small interval around W0. And if we restrict our sample to that subsample, we can do the usual two-stage least square, right? This two-stage least square, but using only the individuals with W between W0 minus a bandwidth to W0 plus a bandwidth. So this is what you can do. And that gives you the local linear two-stage least square estimator. So that's how you use the two-stage least square, the local linear two-stage least square, to get a consistent estimator for the causal effect of a dummy variable in a fuzzy regression discontinuity design. In the next video, we're going to talk about simultaneous equations. And that will be the final topic of this semester.